This homework assignment starts out with a drawing project. You're given the components of a three-dimensional vector and asked to draw that image. And I've told you that that's not really something that I expect you to be able to do very well, but I did want to show you how you can go about doing it if you have to. I've marked the three different axes here, and I'm marking them with the appropriate number of units for each of those three axes, so that we've got the three component vectors all set up here. I want to start with the one on the J, the J axis. Notice what I'm going to do here. This is the segment, and I'm going to draw a line parallel to it over here, because that's where the other edge of the bottom of the box is going to be. Now, again, looking at I, the I axis, this is what's there. This parallel line represents the other edge of the base of the box. So now we've got the base drawn. Here's the height. This is where the top of the box is going to be. Notice I've drawn a line parallel again to the existing one down at the bottom. Again, parallel. These are lines that are parallel, or segments that are parallel to the segments that are already drawn. Now let's take a look at the height. That's the height. So where else are we going to need height represented? Here. And again, we want a segment that's parallel to the axis. Here, parallel to the axis. Here, parallel to the axis. So now, there's still a little bit missing here. What's missing? Well, we've got to get the top of the box drawn. We've got the goal posts, essentially. Now there's the bar. And we need one more going the other way. So here's where we put that in. Okay, we're going to connect the intersections of the red and the green on one side, the red and the green on the other. And now you've got sort of what a box looks like. Okay, let's just color in the whole box here with this dark blue, and then put the vector in where it's going to go. It starts at the origin, and it runs straight up and across to the far corner of the box. Okay, not the best representation, but not so bad. This is what the drawing in the back of the book looks like. The next problem includes two different three-dimensional vectors, A and B, and asks you to add them together. And the way you do that is you literally just add the different components. You've got the I's, the J's, and the K's, and when you add them up, that's what you get. And then it asks you to subtract A minus B, and again, that's what you do. Directly take the two components and subtract them. 4 minus 7, negative 3i. Now you've got 2 minus negative 5. That's going to be plus 7. J. And negative 3 minus k, that's going to be minus 4k. So there's your A minus B. And B minus A is just going to be the opposite. Going in the opposite direction, it's going to be the opposite of A minus B, so you could just multiply that one by negative 1. Or you can go through the motions here, and this is what you wind up with. I'm going to do the pieces of problem 5 in a slightly different order, because I want to just pick up and finish this. We're looking at the magnitude of A plus B, and then the magnitude of A plus the magnitude of B. Notice we're talking about a triangle here. If you have vector A, right, that's this one right here. Okay, so we'll mark that vector A. And then this one's going to be vector B. And then the one that connects the tail of one to the head of the other is vector A plus B. To get the magnitude, we use the three-dimensional Pythagorean theorem, square each of the magnitudes of the components, add them together, take the square root of that, and in this case that turns out to be the square root of 134. Okay? Now if we want to take A, right, the magnitude of A, and add that to the magnitude of B, we're going to wind up with something different. We take each of the magnitudes separately using the three-dimensional Pythagorean theorem, add them together, and then wind up with an answer. The book goes beyond just adding the absolute values. It uses a calculator to find the decimal approximations, but are they the same? No, they're not the same. When we're asked to do the vector multiplication, the scalar multiplication of vector A, multiplying that by 3 means multiplying each of the components by 3. If you want to do something more complicated, take 6 times A and 5 times B and then subtract them from each other. Again, you just do each of the components separately for each of the two different vectors, and then do the subtraction, and here's what you come up with. Here's the scalar multiplication, 3 times A, and then below it here is the combination of 6A minus 5B. Now, as for the unit vector, in order to get the unit vector of B, we need the magnitude of B. What we're looking for is a vector in the direction of B that has a magnitude of 1. And in order to find that, we've got to get the magnitude and then go back and use that magnitude to divide the original vector B in order to get a vector that has a magnitude of 1. So we're going to take vector B, okay? We're going to get the unit vector of it, and we're going to do that by dividing each one of the components by 5 square root of 3. Then, of course, you've got to simplify whatever answer you get, and it looks like this. And the next question says, can we find a vector that is 20, has a magnitude of 20 in the direction of B? And the way to do that is to multiply the unit vector by 20. And that gives you this answer. And you'll notice that the book not only goes through and does the arithmetic, but then uses a calculator to get the decimal equivalents or the decimal approximations of each of the components. So now let's go back and look at this. This one is vector RS. You're given 2 points in space and asked to find the vector from one to the other. And the way you do that is you subtract each one of the components, and that gives you the vector in terms of its components. Now that sometimes is confusing to people, so let's just look at it two-dimensionally. If we're looking for RS, okay, and again, let's just use the first 2 dimensions here. If you draw the 2 points R and S, and you look to see, well, what direction are we going from R to S? It's a positive direction along both of the 2 dimensions we're working with. So that shows you wind up having to subtract S minus R. Okay, and the same is going to be true for the 3 dimensions. Okay. So now let's look at the magnitude of this vector, again using the 3-dimensional Pythagorean theorem. Do the arithmetic by squaring the components, adding them up, and taking the square root, and here's what you get. Now let's take a look at the last problem. It's a word problem, and it's got a bunch of different parts, but the basic problem here is we've got a tree house, okay? And the tree house is at 30, 55, 17, okay, where the dimensions are in feet. Here's what the box looks like. And you can see that you've got the 3 different dimensions. The 17 is the vertical component. So that's going to be the answer to how far above the ground is the treehouse. It's going to be 17 feet. In order to get the distance from the treehouse to the house, you need the 3-dimensional Pythagorean theorem again. These are the numbers. You square them, you add them together, you get the square root. And the answer is about 65 feet. Okay? Now, here's the next part. We've got the wire that stretched from the tree to the point at the top of the back door. And the question here is to get the vector of the displacement from the treehouse to the back door. So you take the coordinates, the different components here, and you subtract them. And you turn it into a vector expressed in component form. And then, of course, the next question is going to be, what's the magnitude of this vector? In other words, how far is the distance from the door to the house? You use the 3-dimensional Pythagorean theorem. That gets you an answer, a little more than 59 feet. But that's not the whole problem. Apparently the message got stuck. So now we've got to figure out how far did it get. It only made it 0.3 of the entire distance. So here's the displacement vector that will show you where the message stopped. We get that by multiplying each of the components by 0.3. And then the question is, how far did it go? One way to do that would just be to take the original number, 59.2 something, and multiply that by 0.3. So we'll do that here and get the answer. But then, just to double check, let's use the 3-dimensional Pythagorean theorem on the components of this smaller vector and see what happens. And of course, no surprise, we get exactly the same number. So here, the next step is to find the displacement vector that identifies the position of the message that got stuck. So what do? We take the 2 vectors and add them together. Why? Well, this is what it looks like. From the house to the starting point where the message started, and then it gets 0.3 of the direction that it's going. Well, that is 2 vectors added together. So we do that in order to get the position of the message. And there are the components. We added them. Now we turn the components into a vector described by its components. We get 24i plus 38.5j plus 14.3k, and that is the answer you're looking for. And by the way, 14.3 is the vertical component, so that's how high off the ground the message is. There you go.